Hey guys, welcome to CCL Biology, the channel for easy to understand biology lessons. If you are a high school student who's looking for some extra help with your general biology or your AP biology class, or maybe you're a college student who's taking that intro bio course, this is the place for you. I am your friendly bio nerd. Thanks so much for tuning in to my channel. In this video, I'm going to be talking all about atoms, particularly subatomic particles, atomic number, and atomic mass. So if you want to get a better understanding of atoms, then stay tuned. While you're here, please hit the like button below if you find this video to be helpful. And if you want more easy to understand biology lessons, then be sure to subscribe to my channel and hit the notification bell to be notified about new videos that go up every week. So again, today we're going to look at subatomic particles and atomic number and mass. Now this does dip into some basic chemistry, so if you need some help in that chemistry area, this video should definitely be helpful for you too. All right, so I do a general overview of what atoms are in my matter, elements, and atoms video, so I'll post a link to that video in the description box below. Just to do a quick recap, atoms are substances that make up elements. It's the smallest unit of matter that still has the properties of an element. So today, let's kind of break into that atom and see what it's made of. All right, so every atom has subatomic particles, meaning particles that are even smaller than the atom. So wait, let's back it up a little bit. I thought you just said that an atom is the smallest unit of matter, right? No, let's be clear. An atom is the smallest unit of matter that still has the properties of an element, okay? So what does that mean? Well, let's say we take the atom of sodium, for instance, or the element of sodium. So if I take individual sodium atoms inside of a sodium element, they would still behave like sodium. You know, each atom would still be, metallic. It would still be highly reactive. It would still have those same properties of the element sodium. But subatomic particles, which are contained inside of an atom, they're considered matter as well because they take up space in the atom and they have mass. So the two characteristics or the two qualities that are needed for something to be considered matter is taking up space and having mass. So subatomic particles are considered matter, but they do not have the properties of the element. So the subatomic particles inside of sodium don't behave like sodium. So that may still be a little abstract, so let's kind of bring it into everyday terms. Let's think about it like one of those, like those double-decker super big sandwiches, okay? So let's say that a sandwich represents an element, okay? So if I were to cut this sandwich into equal parts, each equal part would be like an atom, okay? So if you notice, each equal part still has all of the same properties of the sandwich as a whole, okay? So you see how each part that I cut still has two pieces of bread, still has lettuce, cheese, the meat, yada, yada, what have you, all right? So each individual part still tastes just like the whole sandwich would, okay? Now, if I were to take the cheese out by itself, the cheese would be kind of like a subatomic particle, okay? By itself, it doesn't have the same properties of the whole sandwich. The cheese just by itself, it's going to smell different than the whole sandwich. It tastes different. It's going to look different than the whole sandwich does, okay? But the cheese, along with all the other ingredients, the lettuce, the mayonnaise, the mustard, whatever, you need all of that. They're all necessary to make each cut of the sandwich complete, all right? So it's the same with subatomic particles. By themselves, they're not going to have the same properties of whatever element that they're a part of, but they're necessary. We need all of the subatomic particles to build up the atom, to build up the element. So there are three subatomic particles that we really care about for biology's sake, and those are protons, neutrons, and electrons. So every proton has 1 unit of positive electric charge. So we see that here. And we call it +1. Electrons are the opposite. They are negatively charged with 1 unit of negative charge, so we say -1. Now, neutrons have no electric charge at all. They are what we call electrically neutral, okay? So here's their charge here, and we also see their symbols here. So electrons are typically symbolized by E with the negative sign, a minus sign. Protons are P with the plus sign, and then neutrons are N. Okay? So we also have their relative mass, but we're going to get to that in a second. All right, so let's look at where these subatomic particles are located inside of an atom. So we see that the protons and the neutrons, so here in this picture, the protons are pictured in blue, the neutrons are red, and the electrons are green, okay? So the protons and the neutrons are together in the center of the atom, and that's what we call the nucleus of the atom, okay? So we see those clustered together here. Meanwhile, the electrons, and here it looks like the electrons are the same size as the protons and neutrons, but in real life, electrons are way, way smaller than protons and neutrons. So those electrons, which are way smaller, they swirl around the nucleus, outside of the nucleus, in what we typically call the electron cloud of the atom. So these circles here are representing the electron cloud. And this here again in the center is the nucleus. All right. So in real life, atoms don't have these actual like circular borders. They don't have a real hard, fast border around them. It's like a cloud, all right, with those electrons swirling around. Okay. So that may make you ask the question, well, what keeps the electrons from just swirling and wandering off and flying away from the atom if there's no real border that's keeping them closed in? Well, it has to do with the charges. So remember we just said that protons have a positive charge and electrons have a negative charge. So whenever we're talking about charges, the opposites always attract, okay? So that means that the protons here in the nucleus give the whole nucleus a positive charge overall, okay? Because remember, the neutrons don't have a charge. So electrically, they're not really contributing to the charge of the nucleus. But the protons, since they're positive, they make the whole nucleus positive, okay? And the electrons, which are negative, make that whole cloud area negative. So since we have those opposite charges there, they're going to be attracted to each other, all right? So the negative electrons in the electron cloud are attracted to the positive protons inside the nucleus, okay? So this allows the nucleus to keep a hold of those electrons. So because it's the positive nucleus, so it's attracted to and keeping a hold of those negative electrons. And that's what keeps the electrons in one atom from, flying and wandering off, all right? So the intensity of that hold, so in other words, how tightly the nucleus is holding onto those electrons does weaken depending on how far out the electrons are inside of that electron cloud, okay? So electrons kind of live in what we call electron shells inside of the cloud. So I'm not going to go into depth about electron shells in this video, but I do talk about that in my All About Electrons video. So I'll post a link to that video down in the description box below. All right. So let's go back to the mass of these subatomic particles. All right, so when we're looking at the mass or the relative mass, protons and neutrons are very similar in mass. They both have a mass of about 1 Dalton, and that's the unit of measurement that we use for atoms and subatomic particles, the Dalton, because pretty much all of the other units of measurements that we're used to, like grams or milligrams, they're kind of useless because subatomic particles are so small, so even milligrams just wouldn't really help. So we use a unit of measurement called the Dalton for atoms and subatomic particles, okay? It's also called the atomic mass unit, or AMU. So sometimes you'll see 1 AMU, and that's talking about the atomic mass unit. It's the same as the Dalton. All right, so like I said before, electrons are incredibly small in relation to protons and neutrons. Of course, protons and neutrons are small too, but electrons are really, 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 really small, all right? They're pretty much so small that for our intents and purposes, we don't really care about their mass, in the sense that we don't factor electrons when we're calculating the mass of an atom. So protons, neutrons, and electrons make up an atom, and atoms make up elements, all right? And so every element has its own unique type of atom, okay? So that means that carbon elements have carbon atoms, and silicone elements have silicone atoms, okay? So you may be thinking, well, what makes one atom different from another? If atoms all have the same subatomic particles, which they do, all atoms have protons and electrons and neutrons, then how can a carbon atom be different from a silicon atom? Great question. All right, so let's talk about that. So what makes one kind of atom different from another kind of atom is the proton that's inside of the atom, specifically the number of protons inside of the atom. All right, so let's look at the periodic table here. So if we look at, let's say, carbon, okay? So carbon versus silicon, like I was saying earlier. So the protons inside of a carbon atom, they have the same size as the protons in a silicon atom. They have the same, +1 positive charge. They behave in the same way. But what makes it different is the amount of the protons in these two atoms. They have different amount of protons, okay? So a carbon atom has 6 protons, and a silicon atom has 14 protons, all right? And that's what fundamentally makes them different from each other. A carbon atom that's what makes it different from a silicon atom or a boron or aluminum or any other atom, all right? So, of course, overall, carbon and silicon, they have different masses, they have different chemical properties, they look different, they react differently, but the fundamental primary difference between the two is the number of protons inside of the atom. And that's what makes each atom different from another, is the number of protons. That's what differentiates atoms from each other. We call the number of protons in an atom the atomic number, all right? So if you're looking at an element in a periodic table, the atomic number, like we see here, is usually sometimes written on the left side. Here it's at the top. Sometimes the atomic number is at the bottom left. Sometimes it's even in the center, which honestly is kind of annoying that it's not always in the same place. So here in this case, our atomic number is at the bottom. So we see that the atomic number of carbon is 6, all right? That means that a carbon atom has 6 protons. The atomic number is the number of protons, all right? So that's how you can figure out how many protons are in an atom. Now, what we don't see written here is the number of electrons or the number of neutrons. We only get the number of protons. But that doesn't mean we can't figure out how many electrons or neutrons are in an atom. So let's go to electrons. So we know that atoms are electrically neutral overall. So if an atom does have a positive or a negative charge, then technically it's not an atom anymore. Atoms are electrically neutral. So that means in order for an atom to be neutral, that means that it has to have an equal number of protons, which give that positive charge, and an equal number of electrons, right? So that the positive charge and the negative charge can cancel each other out. So when we look at the atomic number, it's telling us the number of protons, but it's also actually telling us the number of electrons as well. So again, in this case, carbon, the atomic number of carbon is 6, meaning it has 6 protons. And since a carbon atom is neutral electrically, then that means that it has 6 electrons in the atom as well. So that's how you can figure out the number of electrons in an atom. So now we know how to find the number of protons, which is the atomic number, and we know how to figure out the number of electrons in an atom. But what about the neutrons? Well, we can figure out the number of neutrons by looking at the mass number. All right, in this case, it's here at in the top left, and the mass number is the number of protons and neutrons in the atom, okay? Now, honestly, I usually don't see this number that much, like when I'm looking at periodic tables. Sometimes it's there, but I see it rarely. You pretty much are always going to see the atomic number, but the mass number is not always there. Again, it's here in this case, so we see for carbon that the mass number is 12, all right? So how do we figure out the neutrons from there? So if we know that carbon has 6 protons, and we know the mass number, the number of protons and neutrons is 12, then we just do 12 minus 6 to get the number of neutrons, which is 6. So now we know that carbon has 6 protons, 6 electrons, and 6 neutrons. So now again, the way that chemical symbols, the element symbols are represented can be very different. So just showing you here like different examples of how it can vary. Sometimes the atomic number is down at the bottom left, sometimes it's at the top right, sometimes it's at the top left in the center. It just varies, sometimes you have the mass number and sometimes you don't. And then sometimes you get this number here with decimals, okay? So this is called the atomic mass. So we see that here at the bottom. So what if you're trying to figure out the number of neutrons in an atom, but you don't have that mass number? They don't have it, they don't have that listed for you, okay? Well, we can also look at the atomic mass. All right, so if we go back here, remember that both protons and neutrons have a mass of about 1 Dalton. So, but the electrons are so small that the collective mass of the electrons in an atom doesn't contribute to the mass of that entire atom. We don't factor in the mass of electrons when we're trying to figure out the mass of an atom. So the mass of an atom is called the atomic mass, okay? And the atomic mass is equal to the number of protons and neutrons in its nucleus, okay? Or the mass of the protons and neutrons inside the nucleus. Okay, and remember, protons and neutrons, they have the same mass. They both have a mass of 1 Dalton or 1 AMU. So since protons and neutrons have an equal mass, then we can take the atomic mass, divide it into 2, and that'll give us the weight or the mass of the protons and the mass of the neutrons, right? And I'm trying to be careful with saying, weight versus mass, because technically they're kind of different. Weight is influenced by gravity, so it's not, it's not life or death if you use weight versus mass, but mass is technically more correct. All right. So anyway, let's go back to carbon. Okay, so the atomic mass of carbon is 12.011 AMU. All right. So if we divide that into 2, we have 12.011 divided by 2, which gives us 6.0055 AMU. All right, so that means that the mass of the protons in the nucleus of the carbon atom is 6.0055 AMU. And the mass of the neutrons in the carbon atom is the exact same, 6.0055. All right, so, okay, that's cool, but we're still talking about the mass of the neutrons, and we're trying to figure out the number of the neutrons, right? When they don't give us that mass number, we're trying to figure out how to get the number of neutrons, all right? Well, remember, neutrons, one neutron has a mass of roughly 1 Dalton, or 1 AMU. It's pretty much a 1-to-1 ratio. So if that's the case, then if we figured out that the mass of the neutrons in the atom is 6.0055 AMU, then that tells us that there are 6 neutrons inside of that carbon atom. All right, so there we go. So we figured out that a carbon has 6 protons, 6 electrons, and 6 neutrons inside of the atom. And that's typically what you'll see with an atom. You'll typically see equal numbers of all 3 subatomic particles, okay? Now, there are definitely times where you have more or fewer neutrons in the atom than you have protons, okay? And those are called isotopes. I talk about isotopes in my isotopes video, so you can check that out. And you also have cases where you have more or fewer electrons than you have protons, and those are called ions. So you kind of have three different things going on. We've got atoms, which we talked about today, isotopes, and ions, which are related but different. So you can have a different number of neutrons, and you can have a different number of electrons, but the particle that never changes its number is the proton, okay? So, because remember, the number of protons in an atom is what makes one atom different from another. So that number has to stay the same, right? Okay, so if I tried to, add another proton to a carbon atom, I wouldn't have carbon anymore. I would have the next atom up, which is nitrogen, with 7 protons, right? And if I tried to take a proton away from carbon, I wouldn't have carbon, I would have boron. So just remember, the atomic number of an atom will never change, because you cannot change the number of protons and have the same atom. All right, so let's tie this together. Let's have a little recap. So atoms are units of matter, and they contain subatomic particles, which are protons, neutrons, and electrons. And those subatomic particles are matter as well. All right, protons are positive, electrons are negative, and neutrons are neutral. Okay, Protons and neutrons live in the nucleus of the atom, and the electrons swirl around in the cloud of the atom. All right, and then we talked about the atomic number, which is the number of protons in an atom, the mass number, which is the number of protons and neutrons in the atom, and the atomic mass, which is the total mass of the atom. Well, that's it for today's video. I hope it was helpful for you. If it was, then please let me know by leaving a thumbs up in the comments section below. And if you have any remaining questions, then definitely type those questions in the comments and I will be sure to provide an answer. Thank you so much for watching CCL Biology. That is Christ-Centered Life Biology. Thanks and God bless. Bye-bye.